Hello, everyone. So I'm glad to present you today a joint work with Antoine Bommier, Arnaud Goussebaïle, and Daniel Heyen from the ETH, entitled Disagreement Aversion. The motivation for this paper is to guide decision-making under situations of scientific disagreement. So when experts arrive at the same conclusion, but for different reasons, their apparent unanimity is spurious, yet existing models operate as if they agreed. We propose a decision rules that can model any kind of aversion to disagreement between experts, including the cases of spurious unanimity. To explain you this, let me show how it works in a stylized climate example. So let's say the decision maker faces two options, either quick decarbonization, fast net zero, or geoengineering, solar radiation management, as a way to buy time in the fight against climate change. So here are the different states and payoffs and beliefs. So the decision maker doesn't know well or precisely what the outcomes of the different choices will be and resort to experts to know these probabilities. All experts agree on what will happen in the net zero scenario. It is a costly and safe policy that will yield utility 0.5 in all states of the world. Experts disagree on what will happen with geoengineering, SRM. Expert 1 thinks that it will be as costly and as safe as the net zero scenario. Expert 1 puts probability 1 on the probability that the neutral state occurs, where SRM provides utility 1.5. And expert 2 thinks that actually geoengineering is risky and think that it can yield a catastrophic consequences with probability 1/2, and it could provide the costless solution also with probability 1/2. For both experts, both choices have the same expected utility, 0.5. So both experts are indifferent between net zero and geoengineering. What should we do as the decision maker in this situation? First principle to guide our decision is the unanimity principle. Because both experts are indifferent between net zero and geoengineering, then the decision maker should also be indifferent between the two. Yet, this unanimity is somehow spurious, right? Because there is an underlying disagreement on the distribution of outcomes that SRM can yield, and there is no disagreement on net zero. So this disagreement for geoengineering may indicate a lack of robust scientific understanding of this choice. And if as a decision maker we are cautious, we may actually be averse to such disagreement, in which case we will prefer net zero. Why would we be averse? Because maybe this disagreement suggests that the distribution of outcome, the true one, could be worse than what any of the experts can imagine. For example, if the bad state can actually occur with probability 1.5, as expert 2 thinks, and the good state cannot occur as expert 1 thinks. We make 3 contributions with this paper. The first is to introduce a novel notion of disagreement aversion. The literature, until here, addresses this question of the cautious aggregation of experts' belief with ambiguity aversion models. Ambiguity aversion is a preference for unanimity in terms of expected utility, what we call utility consensus. But these models do not pay attention to cases of spurious unanimity, just as in our example. So we push ambiguity aversion one step further and introduce disagreement aversion, which is a distribution for consensus on the whole distribution of outcomes. So we go at a finer level to evaluate what we mean by consensus. The second contribution is to derive a model that allows to account for disagreement aversion. So common ambiguity models aggregate expected utilities provided by the different experts. So the expected utility seen by expert 1, so the beliefs P1, until the expected utility seen by expert N. And they do so by taking a pessimistic aggregation using this function I. Okay, this encompasses all models of ambiguity aversion. And these models respect the unanimity principle. When we relax this principle, that is known as the monotonicity axiom in the theory, we can obtain another models. And instead of aggregating the expected utility of experts, we aggregate their probability corresponding to the distribution of outcomes that the choice can yield. And yes, this is the condensed formula. We can do it with the same aggregator I as with ambiguity models. The difference is that we don't operate the aggregation at the same stage. We will show that our distribution aggregating model is more disagreement averse than the expected utility aggregating model, because actually the expected utility aggregating model are not disagreement averse. And our models are also more ambiguity averse in a sense. Our third contribution is to draw the implication of disagreement aversion in concrete applications like climate change. We will show that when we increase disagreement aversion or ambiguity aversion, the optimal choices will be more cautious. It may seem weird, but we don't have this result in ambiguity aversion models, because these models need extra assumptions that are somehow unrealistic to obtain a similar result. So why do we care? Well, uncertainty surrounds a number of questions, such as climate change, portfolio choice, or the choice of a treatment like a vaccine in a pandemic, the choice of the policy in a pandemic, or macroeconomic policy. In all these cases, we don't know precisely what are the consequences of our choices, and we turn to experts that have different beliefs regarding these choices. The curve that you see on the right shows you the climate sensitivity, distributions of climate sensitivity according to different experts or different climate models. The climate sensitivity tells you how much the Earth will warm for a doubling of the concentration of CO2 in the atmosphere. So it's around 3 degrees, but there is a large uncertainty. The model do not agree. And we can use our model to aggregate these different experts' beliefs in a cautious way to take a decision regarding the optimal level of abatement in climate change.
Adrien, may I ask a question?
Yes,
so
sure.
in that, it means here, to understand well, it means that what you call expert is not individuals. It might be just studies, models. Here, one expert is a distribution in a sense. So what I call model uncertainty, this is really that, well, a distribution, for example. In that case, it seems to be that, right?
Yes, we call it expert. We could call it model. You are right. Yeah. We call it expert because the only thing that we look at is a distribution function or a distribution rather on the states of the world. So it's not a structural model with parameters, etc.
Yeah, sure. Yeah. Okay.
But and by the way, a precision, we assume away any strategic concern. So in our model, the experts are assumed to have the same objective as the decision maker. So another way to see it is that the expert only provides their belief in a truthful way,
okay,
not their utility. Yeah. If there is no other question, I'll turn to the definition, then show the properties of our model, and the consequences on concrete applications. So to explain you the definitions, I'll try to show how they relate to our introductory example. Our set of outcome is taken as a closed interval of R, of real numbers for simplicity. Then we consider a set omega of states of the world. So the states of the world in the example are the bad state, the neutral state, and the good state. And the outcomes are 0, 0.5, or 1. But you can imagine any outcome between 0 and 1. A choice, also known as ACT in decision theory, is a mapping from states of the world to outcomes. So in our example, there are two choices, the net zero scenario and the geoengineering scenario. A choice, I mean, we has a k alpha different outcomes in its image, and we denote alpha 1 until alpha k alpha, the ordered image of this choice. So the image will be, so k alpha would be 1 in net zero and alpha 1 0.5. And for SRM, it will be alpha 1 equals 0, alpha 2 equals 0.5, alpha 3 equals 1. Then some choices yield the same outcome in all states of the world. We call them sure choices, and we simply denote them by the outcome they yield, so X. In our case, a net zero is a sure choice. We have different experts, and we denote PI, expert I's belief, which is their subjective probability measure on omega. So for expert 1, P1, their belief is this, so probability 1 on the neutral state, and for expert 2 is this one, so probability 1/2 on the bad and on the good state. We consider n experts, and we call the expertise the collection of all experts' belief. And our domain is choices, so we're interested in preferences over choices. And what we call a decision rule is a way to form preferences given an expertise. So it's a mapping from expertise to preferences over choices. Now, a choice alpha will always be evaluated using one type of information. It's the probabilities that experts see regarding the outcomes of this choice. So the only thing that matters to assess a choice will be the distribution of outcomes, and we will work with the decumulative distribution of outcomes of this choice. So this cumulative distribution of the choice alpha as seen from expert I is defined in this way. So for the kth lowest outcome in its image is the probability that alpha yields an outcome at least as high as alpha k. Are there questions on these definitions? Good. The first assumption we make is about risk preferences. So here we are in the simple case where there is no disagreement. So you can see it as either there is just one expert, P1, or all experts have the same belief. Okay, and in this case, in absence of disagreement, we assume expected utility. So this is the formula of expected utility using our notation. It's the sum of utility of outcome alpha k times the probability that this outcome obtains, which is the difference of the decumulative distribution function. And notice that we can rewrite this formula using a summation by parts, where instead of taking the difference on probabilities, we'll take it on utility levels. Okay, and this will turn out to be more practical for our purpose. Just a precision, we work with a decumulative distribution function instead of cumulative distribution function because we want to have results of disagreement aversion in terms of concavity rather than in terms of convexity, which we find more appealing, but yeah, it's equivalent. So we assume expected utility when there is no disagreement. And now we need to think of what we mean by disagreement, by unanimity. There are two different notions of consensus. The weak one, the one used in the literature so far, is utility consensus. So we say that a choice alpha is expected utility consensual when all experts agree on its expected utility level. And then we introduce a stronger notion, which is distribution consensus, where a choice alpha is distribution consensual when all experts agree on the whole distribution of its outcomes. So they agree on everything that matters for us. All existing models of ambiguity aversion can be written in the following form. This is a result from a paper from Seria, Vioglio, and co-authors. They can be written as an aggregation of the expected utility of this choice seen by the different experts. And the aggregator I has some basic properties, such as when all experts agree on the expected utility level, then the decision maker also evaluates this prospect with the same expected utility level. And it's continuous and increasing. But this aggregator can be, for example, an arithmetic average, or it can be something more pessimistic than that. Here are some examples of aggregator. The simplest case is the arithmetic mean. Okay, this is linear pooling. This is the benchmark in the literature. And in this case, there will be no aversion to ambiguity. It's a perfectly valid way to aggregate experts' beliefs. It will not be a cautious way, but it is the Bayesian way. So it is appealing by many aspects. Now, if we want to introduce some caution, we can take aggregators I that brings a result value lower than the arithmetic mean. For example, the minimum of this component, which is the simplest case of the max-min models produced by Gilboa and Schmeidler. Or we can take a smooth aggregator. If you take a concave function psi by summing the concave transformation of the component. This is the smooth aggregator, the simple version of the smooth aggregator introduced by Klibanov, Mukherjee, and Mainacci. So just to give you a visual example of how this aggregator works, in colors you have the different utility levels, and in black you would have the I of these utility levels, so the aggregation, which here is lower than the arithmetic mean 0.5. And by giving more weight to lower utility levels, you are being cautious when you evaluate a choice. You think more of what can happen in the worst cases and discard the best cases. In our introductory examples, both experts agree on the utility level. It's 0.5. This is what we call spurious unanimity, because in reality they don't agree on everything. And in this case, whatever the aggregator I, the decision maker will also arrive at the conclusion that both choices have utility 0.5. Now let's define disagreement aversion. We say that a decision rule is disagreement averse if, when you consider choices alpha on which there is disagreement, in the sense that they are not distribution consensual, then you will prefer sure outcomes to these choices. What sure outcomes? Well, if all experts agree that a sure outcome X is as good as alpha or better than alpha, then the decision maker will strictly prefer the sure outcome to alpha because there is no disagreement in the sure outcome. It's interesting to compare this definition to the Pareto condition. The Pareto condition says that if a choice alpha is weakly preferred to a choice beta by all experts, meaning their expected utility is higher or equal, then the decision maker should also weakly prefer alpha to beta. And this is in stark contradiction with disagreement aversion. Any model that exhibits disagreement aversion cannot be Paretian. And to see this, take beta as a sure outcome X. I mean, take alpha and beta, such as beta is a sure outcome X, which is indifferent to alpha for all expert I. Then, due to disagreement aversion, X will be strictly preferred to alpha. And if you think you can also be Paretian, then alpha will be weakly preferred to X, which is a contradiction. Any question? Okay. Notice that our definition of disagreement aversion was an absolute notion that doesn't depend on a benchmark level, say. This is in contrast with the literature on ambiguity aversion, where the ambiguity aversion is usually defined in a comparative way. And to define an absolute notion, you need to define a benchmark case of ambiguity neutrality. We also define comparative notions. So we say that a decision maker A will be more disagreement averse than a decision maker B if for all choices alpha on which there is disagreement that are not distribution consensual, then B, so the less disagreement averse, will evaluate the non-consensual choices at a higher level X than A. The definition of comparative ambiguity aversion is very similar. The only difference is that we consider choices that are not utility consensual instead of choices that are not distribution consensual. And this is the definition used in the literature. Now we can define our model, which we call distribution aggregating rule. We say that the decision rule is distribution aggregating if it is written in the following way. So first you aggregate the cumulative or decumulative distribution provided by the experts. And this I of P is an equivalent probability distribution if you want to evaluate choice alpha. So we first build this equivalent cumulative distribution function for the choice, and then we take the expected utility. And we can compare this to expected utility aggregating rules, where the aggregation occurs at a later stage. So first you take the expected utility according to each expert, and then you aggregate them. Let me show you visually what it means to be distribution aggregating. So these are the decumulative distribution function for geoengineering according to our two experts. So expert one thinks that there is probability 1 that the utility will be at least 0.5. And expert 2 thinks that there is probability 1/2 that is probability 0, so that it's at least 0, and probability 1/2 that it will bring utility 1, so probability 1/2 that it will be at least 1, and probability 1 that it will be at least 0. Now, if we aggregate this decumulative distribution function in a disagreement averse way, we will take point by point pessimistic aggregation of the two curves, the blue one and the orange one. So here and here will be below the midpoint, here and here as well, here as well, etc. If we didn't choose a decision, if we were not averse to disagreement, we would aggregate the two discriminative distribution function at the midpoint. Okay, take the arithmetic mean of the two experts. And if we are extremely disagreement averse, we'll consider the minimum of the two curves. So we'll consider expert 2 on bad state and expert 1 on good state. We'll take the most pessimistic view, outcome by outcome. What are the properties of our model? We show two sufficient conditions for disagreement aversion. The first one is that our aggregator I is strictly concave. And another way that is sufficient to be disagreement averse is to take an aggregator I that is below the arithmetic mean. An arithmetic mean, actually, because you can weight the experts. We also characterize comparative notions, and a decision rule A is more disagreement averse than a decision rule B if and only if its aggregator IA is below the aggregator of B. This is valid for distribution aggregating rules because expected utility aggregating rules cannot exhibit disagreement aversion. So a fortiori, they cannot exhibit more disagreement aversion than one another. Comparative ambiguity aversion is characterized by the same property. A is more ambiguity averse than B if the aggregator of A is below the aggregator of B. This is valid for both the distribution aggregating rule and expected utility aggregating rules. And you see that if you are using the distribution aggregating models, you will be disagreement averse if A will be more disagreement averse than B, if and only if A is more ambiguity averse than B. Let's think about the link between distribution aggregating rules and expected utility aggregating rules. Here we show two propositions. The first one is, roughly speaking, that distribution aggregation is more cautious than expected utility aggregation. And the second one, then the intersection between distribution aggregating rule and expected utility aggregation rule is the linear pooling. So what we mean more precisely by the first proposition is the following. If you take a given utility index U and a given aggregator I, and you define the distribution aggregating rule and the expected utility aggregating rule that use this U and this I, if in addition you take I as strictly concave, which is the case in all practical application, then the distribution aggregating rule exhibits more ambiguity aversion and more disagreement aversion than the utility aggregating rule. The second proposition says that the only way that you can be Paretian if you are distribution aggregating is to have a linear aggregator, so to not exhibit ambiguity aversion or disagreement aversion. It's to be Bayesian. A way to summarize the first proposition I've just said is with this diagram. The benchmark case is linear pooling, where you are not cautious. You form subjective utility. The decision maker forms their preferences by taking a linear average of the expert's belief and is a subjective expected utility maximizer. Then you can take more caution by using expected utility aggregating rule, and this increases ambiguity aversion. Now, if you take a distribution aggregating rule, you will increase ambiguity aversion and disagreement aversion even further, at least when I is strictly concave. We provide a representation result. That is to say, we axiomatize our model. The main axiom are the following. Where there is no disagreement, when all experts have the same belief, we take expected utility risk preferences. The important axioms that depart from the literature is and weakens monotonicity is monotonicity with respect to first-order stochastic dominance. What it means is that if a choice A is seen as, if the distribution of outcomes of a choice A dominates that of a choice B for each expert, in the sense that the decumulative distribution function is always higher, then choice A should be preferred by the decision maker. This is weaker than monotonicity, which is assumed in ambiguity aversion model, where decision maker should prefer A to B as soon as the expected utility of A is higher than that of B according to each expert. Then there is the commotonic shortlisting principle, which I can explain, but if you want, but just to give you a rough sense, it's to put more structure in our model. A continuity axiom as usual. And we add a last axiom, which is that disagreement aversion is independent from the level of the outcome, which is optional, but allows to have a simpler formula. And now let's talk about how our model can be applied and how it will be useful for applied work. So in this section, we consider that the ex post utility has the following form. It's a function of a choice variable A, the action, and a contingency omega. That is to say, our states of the world omega are now ordered from the worst to the best. You can think of omega as climate sensitivity, or rather the opposite of climate sensitivity, so climate insensitivity. So the higher omega, the less the Earth will warm following CO2 emissions. And A as abatement, okay, if we think of climate change. Now let's show our main result of this section using graphical illustrations. So let's take simple example, which is the same as the introductory example, but this is for tissues. And so here we have both experts that see the expected utility at 0.5. Okay. Now let's consider the case where the cross derivative of u has a constant sign, in this case negative. What it means is that when we increase the action, abatement say, then the dispersion in the expert's utility levels will be reduced. Okay, delta du over d omega is somehow this delta u that we had before, and it means the gain of utility by between the different states of the world. So when we increase the abatement level, climate sensitivity will be less of a concern, and this materializes as this condition. What it means graphically is that the curve will get closer to each other. So for example, this abatement A, the minimal. Okay, so this is what happens when we increase A. And when we use the distribution aggregating rule, and we will prefer around the optimum to increase A when we increase disagreement aversion. This is because we are more sensitive to reduction of the likelihood of bad states than reduction of the likelihood of good states. So higher disagreement aversion in the distribution aggregating model would lead to an increase of the action abatement in this case. In terms of expected utility, what happened is that we were at the beginning at the same expected utility according to each expert, but now we introduce some dispersion by increasing A. And so if you take now the expected utility aggregating rule, what matters is the level and the dispersion in expected utilities. And if you increase ambiguity aversion, then you'd rather decrease abatement than increase it in this example. Because if you increase abatement, then you increase the dispersion. And when you are more ambiguity averse, you are more sensitive to the dispersion. So you would rather go in the direction of reducing the dispersion. So in the trade-off of here having a higher expected utility on average, if we take the average of the two experts, and having more dispersion, when we are more ambiguity averse, we will prefer to reduce the dispersion, so we would not want to increase A. So we don't have this result as in the previous case that increasing ambiguity aversion will lead to an increase in A at the optimum. In this example, we would rather decrease A, but we could show other examples where we would like to increase A. We don't have a neat result as in the distribution aggregating rules. Can't we have a similar result for ambiguity aversion models for utility aggregating rules? Well, we can if the experts are ordered in terms of first order stochastic dominance, meaning that they are ordered in terms of optimism. So take another example where expert 2 discriminative distribution function is everywhere below expert 1's distribution function, which means that expert 2 is more pessimistic than expert 1 for any outcome. In this case, the expected utilities seen by each expert look like that. And in this case, when we increase A, we increase abatement, we will again put the decumulative distribution function closer. But yeah, this will also put the expected utility closer. Okay, this is a consequence of having the experts ordered. Getting the curves closer will necessarily getting the expected utility closer. And in this case, when you increase ambiguity aversion, then you will prefer to increase A. Because here, what happens if you increase A is that you decrease the dispersion and you also decrease the average expected utility level. But when you increase ambiguity aversion, you are more sensitive to reducing the dispersion. So around the optimal, you would rather favor increasing A when ambiguity aversion increases. Was it clear? We show this using the climate example by doing some just a out-of-the-hat calibration, just an illustrative purpose. And we show that in the expected utility aggregating model, when experts are ordered in terms of first-order stochastic dominance or in terms of optimism, More ambiguity aversion leads to more abatement, which is intuitive, but it's not the case when they are not ordered in terms of optimism. To summarize, when we assume a constant sign cross-derivative for our utility index, we have a simpler result in the distribution aggregating case that decision maker A is more cautious than B, in the sense that A is more disagreement averse and more ambiguity averse, at the sole condition that their aggregator A is below the aggregator of B, IB. In the expected utility aggregating case, we not only need this condition, but we also need to get the same result that experts' beliefs are ordered in terms of first-order stochastic dominance. And also that they are KMM. I mean, it would probably work with other functional forms, but to prove the result, we need a specific functional form. And this ordering of experts in terms of first-order stochastic dominance is not really realistic. When you think of the first graph I showed on the distribution of climate sensitivity, they were not ordered in terms of first-order stochastic dominance. Now let's compare with our example what may happen when we increase ambiguity aversion with the utility aggregating rule and the distribution aggregating rule. With the utility aggregation rule, we may decrease the optimal abatement when the experts' beliefs are not ordered, whereas with the distribution aggregating rule, the optimal abatement will always increase. We always take more cautious decision in the distribution aggregating rule. So we could, I mean, depending on the example, we could also have an increasing blue line here, but everything can happen. Also note that dotted line are the optimal abatement level from the point of view of each expert. And in the distribution aggregation rule, when the disagreement aversion is especially high, we leave the convex envelope of the experts' optimal choices. The optimal choices can be above both what experts would recommend. This is because we violate the unanimity principle that we are able to exhibit such a phenomenon. In the utility aggregating rule, we will converge when ambiguity aversion is very high to the optimal abatement recommended by the most pessimistic expert on expected utility terms. And when this expert is more pessimistic in expected utility terms, but not everywhere on the distribution, then it may be the case that more disagreement aversion leads to an action to change the action in the direction opposite to that when you increase ambiguity aversion in ambiguity aversion models. Are there questions? Okay, let me explain how this paper connects to the literature. So first, we provide an alternative to expected utility aggregating rules, so that are used in the ambiguity literature. These models are monotonic in the sense that they are paration. It's another synonym for unanimity principle. And they aggregate utilities. The first example was max-min by Gilboa and Schmeidler, which built upon the rank-dependent utility from Quiggin. We can also cite robust control, smooth ambiguity preferences that are quite popular, the KMM model, and variational preferences, more generally vector expected utility. all these are of the expected utility aggregating form. The exception is in this literature is a paper from Antoine Bommier, on which we build. We also contribute to the aggregation of conflicting beliefs. So here the benchmark is linear pooling, where there is no caution in the aggregation of belief. When there is caution, it's usually done with ambiguity aversion models. And some recent refinement operationalize, for example, the max-min decision rule to explain what sets of belief should be considered when we increase aversion to imprecision. Then recent development also account for within experts ambiguity together with between experts uncertainty. And an important papers in the literature are contribution by Seria, Violio, and co-authors that address a model misspecification as another source of uncertainty than the fact that we don't know what model is best. Here, each model can be wrong. So this is close to our model in a sense where each expert could be wrong. And this departs from the ambiguity aversion literature, where we know for sure that one expert is right, and this justifies the unanimity principle. So in their model, actually, they are not always disagreement averse, and there are not always paration. So yeah, it's another way to so they will be averse to model misspecification, but not they will not use like us the fact that a disagreement between experts may indicate a model misspecification. For them, the level of misspecification considered is taken as given. Then there are other papers like a recent contribution by Stanka that preserves the Pareto principle but relaxes other axioms when aggregating experts. So in relaxing the Pareto condition, we follow papers that have criticized this condition. For example, Gilboa, Salmet, and Schmeiler say that society should not necessarily endorse unanimous choice when it is based on contradictory belief. And Mongin was the first of talking about spurious unanimity, saying that it need not be preserved at a collective level. Even though the spurious unanimity he talks about is not really the same as us. It's spurious in the sense, and the same for Gilboa, Salmet, and Schmeiler. It's spurious because there are conflicts in taste and conflicts in belief, and the two may spuriously reconcile. In our paper, we don't have conflict in taste. And I think most importantly, our paper is relevant for applied work like portfolio choice, savings decision, climate change, pandemics. All these models use ambiguity aversion models, and they have to make this unrealistic assumption that experts are ordered to obtain the intuitive result that when you increase aversion to ambiguity, you will take more cautious choices. So we think that our model is simpler and provide this more intuitive property that you obtain these results whatever the experts' beliefs are. 3 take-home messages. First one is that we provide a new decision rule which aggregates probabilities instead of aggregating expected utilities. Okay, we form a certainty equivalent probability distribution of outcomes to evaluate a choice. Second, our model is sensitive to disagreement over underlying beliefs and not only a lack of unanimity on expected utilities. And third, our model yields intuitive results for disagreement aversion under very mild assumptions. Namely, that when you increase disagreement aversion, you take more cautious decisions. Thank you very much. And you can have a look at the working paper at this address and the slide of this address.